Welcome back to the Physics Dojo. I'm Barry Panis, and today we're going to look at projectile motion. Okay, let's see if we can make sense of projectile motion, starting with what we're familiar with. I've already made a little simulation here showing a ball that's on some kind of a surface. Now the surface is anchored, it can't move, but the ball is moving. The ball has a velocity of 5 meters per second to the right. Now, it's a pretty simple simulation. It's just uniform motion, but let's start with this. Okay, I'm going to run the simulation, and we see that the ball moves. Moving along, nice and steady. The velocity is not changing. We've looked at this before. We're experts at this. We can address this motion with one equation, v equals d over t. All right, now, being as familiar as we are with that, let's move on to the next level. I've already created a second ball. It was hidden off screen up until now, but it's here. Now this ball's not on the ledge, and it's not moving at 5 meters per second. This ball has a velocity of 0 initially, but not being supported by anything, it's going to fall. I'll run the simulation again. And we do. We see it fall faster, 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 faster. Let me get the velocity vector on so that we can actually see that. As it falls, it goes faster and faster and faster. It's actually accelerating at 9.8 meters per second squared. So if it falls for 1 full second, it will have a velocity of 9.8 meters per second. Now again, we've looked at this motion before. We've looked at accelerated motion before. We have 5 equations that address it. Vf equals vi plus at, and so on. So we've seen each of these two motions separately, uniform motion and accelerated motion. Projectile motion builds on that. And to show you what I mean, let me take a copy of this ball, the one on the ledge. Let me just kind of slide it down here so that it is underneath that one and to the right of that one. In fact, I'll get the positioning just right by zeroing it. Perfect. Now I'm also going to show some grid lines so that we can actually see how things line up right now. As you can see, these two balls are lined up left-right, and these two are lined up vertically, up-down. Both of these have a velocity of 5 meters per second, whereas this one has a velocity of 0 initially. However, gravity is going to affect both of these. Let's see how it plays out. Let's just watch the simulation. Press run, and off it goes. So, whereas the other two, this one and this one, are moving in a straight line, this one is going horizontally to the right, and this one's going vertically down, this one followed a curved path. Now, it's a bit of a complicated curve, but in a way, kind of nice. Let me show you the curve. Okay, I'm going to shut that velocity vector off because it gets messy if I leave that on, unfortunately. And I'm going to ask the program to track that one. I'll track it, and I'll track, let's see here, tracking every 32 frames. So what it's going to do is it's going to leave a permanent imprint of where this ball was every 32 frames of the animation. It'll look like there's several of them, but really it's just a kind of a track of where it went. So let me run that simulation again. Okay, so as this ball moves, it leaves kind of a record of where it was. And I'm going to stop the simulation there. You'll notice that it is moving to the right steadily. And you can actually see that here because each of these balls, if you just look at its left to right progression, is actually exactly the same. However, as time goes on, it drops further and further and further and further. This shape here, although it's only a portion of one, is actually a parabola. So the trajectory of a projectile here is actually parabolic. Okay, I'm going to reset that, get rid of the track, and also get rid of tracking. I don't need that right now, so tracking off. Let me get that velocity vector back on. Let's talk about velocities here a little bit more. Okay, so this one has a velocity of 5 meters per second, velocity of 5 meters per second, velocity of 0. Let's run the simulation again up to, oh, I forgot to turn on that velocity vector. Not a problem, we'll turn that on. There we go. Press run. There we go. So, as time goes on, it falls faster and faster and faster. I'm going to stop the simulation. Let's just compare their velocities. Right now, this one has a predictable velocity of 5. That never changed. This one at this moment in time has a velocity of 8.026. And this velocity seems to be completely different than both of those other numbers, 9.456. Okay, what's going on there? Where did that 9.456 come from? Well, you can actually check yourself if you want to. If you were to take this velocity of 5 squared, and the velocity here, 8.026 squared, if you were to sum those two, add them up, and take a square root, I'm pretty sure that you're going to get something that at least rounds off to 9.456. That's because this ball actually has that same velocity of 5 meters per second to the right, and whatever that velocity was a moment ago, and I reset that because I wanted to actually show you it. All I have to do is ask for the program to show me the components of the velocity vector. Now this can get a bit messy. The velocities start to overlap each other as the numbers are close, but that's fine. I'll just run the simulation and show you exactly what I mean by that. So I'll run the simulation. And again, I'm going to choose just some random moment in time here. Okay, now this ball has a velocity of 5 meters per second to the right, that horizontal velocity. It has a velocity y component of, well, I wish it would say 0, but there's little kind of round-offs in the program. So I'm going to call it 0 even though it's displaying something slightly more than 0. This ball is moving constantly to the right with 5 meters per second. At this moment in time, this ball still has a velocity x of 0. It's not going left or right at all. And at the moment, it has a velocity y of 8.761. Aha, but let's have a look at this one. This is the overall velocity, 10.088 at this moment. And we can actually see its components. It's resolved it for us. 5 meters per second to the right, 8.761 to the, well, in the downward direction. And you can see now what I meant. The vertical velocities match up. And similarly, the horizontal velocities match up. Now, this isn't true of just the case that I kind of drew up here. If I take these two and drop them down, just give myself a bit more space to work with, let's say that I give them both a starting velocity, not 0, in the y. So let's give them both a velocity upwards of whatever, 8 meters per second. Okay, so this ball here is going up at exactly 8 meters per second. The display is overlapped, but that's all it is, Vy of 8 meters per second. This ball also is going up at 8 meters per second, but it still has its horizontal velocity of 5 meters per second, resulting in an overall velocity of 9.4 and then some. Now, again, when I run the simulation, watch what happens. They both rise. They both reach their highest point at the same moment. They both fall down, and there's a perfect synchronization. I can go to any moment in time here, I can go anywhere I want, and you'll see that they were always, always, always together vertically, these two. Meanwhile, these two were always, always, always together horizontally, left, right. Okay, now here's the huge significance of this all. If we wanted to mathematically study this projectile, we could resolve its motion into two parts. We could resolve it into a left, right, or horizontal component, and recognize that the physics, the math that we've already developed for uniform motion, applies. In other words, horizontally, I only need one equation to deal with the projectile. V equals d over t. It moves left and right constantly. Now, when we study forces a little bit later, we'll actually understand exactly why that's true. But for now, I'm just going to say that in the idealized case, there's no air resistance or anything else messing up my projectile. It will move horizontally constantly. Meanwhile, vertically, just like an object that is just moving straight up, straight down, the acceleration is from gravity 9.8. So it is for a projectile. The vertical will be accelerated down at 9.8 meters per second squared on Earth, just the same as any other object that's thrown up or down. And that means that we can use our 5 equations for accelerated motion in the vertical, up, down. Let me show you what I mean by that by actually looking at a kind of a typical problem, pen and paper. Okay, so let's summarize. A projectile moves through the air in a parabolic path, and when it does so, it moves horizontally with a constant velocity. One equation is needed, v equals d over t, and at the same time, vertically accelerates from gravity, 9.8 meters per second squared, near the Earth's surface. 5 equations are available to us. So let's have a look at a couple of examples to see how this can all be put together. Okay, so I've already prepared a couple of examples to work through to see if we can make sense of how this all works. Okay, let's get into this. The first example is this. A ball is thrown horizontally at 12 meters per second from a height of 2 meters above the floor. Find how far it moves horizontally before it hits the floor. Okay, let's start with a basic diagram here. So there is a floor, horizontal, and 2 meters above it there is initially a ball, 2 meters above the floor. Now the ball was thrown to the right, I'm just going to assume, at 12 meters per second. Okay, now what the ball is going to do is follow a parabolic path down to the ground. It's going to strike the ground somewhere. I don't exactly know where, but of course that's the whole point of the problem, is to find that. How far did it go horizontally before it strikes the floor? Okay, now we're going to separate this into two components. Horizontal, which I'll call x, and vertical that I'll call y. And I'll even use colors to help separate that. So let's see here. How about if I use green for the vertical? Okay, let's get started here. In the vertical y, what do I know? Well, the ball never rose in this particular question, so I'm going to let down be my positive direction. And I know, of course, that it's going to accelerate from gravity. I assume that we're near the Earth's surface, so 9.8 meters per second squared. I know it's going to fall all the way down to the ground, so that's my d equal to 2 meters. What else do I know? Let's see here. Oh, yeah, the ball was thrown horizontally. Now, I know that it has a velocity of 12 meters per second, but that was horizontal. Initially, in the vertical, it's not moving. It wasn't thrown upwards. It wasn't thrown downwards. It has no vertical velocity in the beginning. That 12 meters per second is going to show up right away in the horizontal, but not yet. Okay, now let's see here. You know what? That's actually enough information to find the final velocity when it strikes the floor in the vertical, but that doesn't interest me now. If I find the time, I could use that in the horizontal because time is the one thing that these two components are going to share. They move together. So however long it took this object to get to the floor, that's how long it's been moving horizontally. So time is kind of a priority for me right now. I'm going to try to find it. So let's see here. I'm trying to scroll. There we go. It's a little bit better. I'm going to set up a kinematics equation. Let's see. It doesn't have a VF in it. So of my 5 acceleration equations, I'm going to use D equal to VIT plus a half AT squared. Now, in this particular case, I definitely benefit from the initial velocity being 0. So the math becomes a little bit easier. I just have d equal to 0.5 AT squared, and I'm looking for t. So I can take the d, divide the 0.5 a down, and that leaves me with a t squared. Or, in other words, solving for t is equal to the root of d over 0.5 a. Now, I know that the d was, just to remind myself, I'll scroll back to my picture, 2 meters. Yep. So the d was 2. There's my 2. The acceleration, 9.8. Okay, so the root of all that. I do have my calculator handy, so I'm just going to punch that in. Let's see here. Square root of 2 divided by, I'm going to use brackets here for my denominator, 0.5 multiplied by 9.8. That's in brackets. I've also used brackets for the square root. So I'm getting a time of 0. I'm just going to record 5 figures should be enough. So 0.6388. That would be 4 sig figs. The first 0 doesn't count. So I'll grab one more. It's a 7 on my calculator, but I'm going to round it up to an 8 because the next digit is a 6. So I'll round up. So 0.63888 seconds. That's how much time it takes this projectile. 0.6388 seconds. That's how much time it takes this projectile to get down from here to the floor. Now, of course, meanwhile, it's been moving sideways. So let me address that horizontal here. Let's see. I'll continue to work in red for my horizontal here. So let's see here. In the horizontal, there we go, x, I am going to say that I now know it's moving at a velocity of however fast it was thrown, 12 meters per second. That's how fast it was going sideways, and that's how fast it will remain. Notice that I'm not putting a VI here for the initial. It actually is the initial, but it's also going to be the final. It's also going to be the in-between. It moves horizontally with a constant velocity. I have no need to call it VI. I know that the time that it takes is this time down here, 0.63888 seconds. 0.63888 seconds. The time is synchronized. However fast it moves, for how much time it moves horizontally, that's the same as how much time it took to move vertically. I'm looking for how far it moves sideways, so that's my d. In my horizontal, I only have one equation, one that I need. V equals d over t. I can solve that for d algebraically. D is equal to v times t. I can put my known values in. Let's see, the v was 12. The time of 0.63888. So, again, grabbing my calculator, multiply that out, and I'm getting something that I'll round off to 3 figures because this really is my final answer. So I'm going to say that that is 7.67 meters. That's my answer. This projectile, right here, this projectile took 0.6388 seconds to move through its arc, and in the process, it dropped 2 meters vertically, but it also moved horizontally that far, 7.67. That's the end of the first example. We found exactly what we're looking for. Let's move on to another example. Okay, example 2. The bullet here, there's a bullet, it's fired horizontally at 250 meters per second towards a wall that is 10 meters away. Find how much it drops before hitting the wall. Okay, I always like to have a little sketch here. So in this case here, I don't really know where the floor is. It doesn't seem to be relevant to this question, but I do know that there is a bullet. Okay, so here's the bullet. Again, I'll just draw it as a little ball, little round thing. And I know that there's a wall somewhere. The wall is out here, 10 meters away. Now, this bullet's actually moving really fast, 250 meters per second. I don't think it's going to drop very much on its way to the wall, but I'm going to draw it exaggerated a little bit. I'm going to show that it does indeed fall in a parabolic arc to the wall. Now, by the time we get to the answer here, you're going to see that it didn't fall very much. But nonetheless, I like my diagram to be clear with what I'm looking for, so I don't mind exaggerating things a little bit for my own benefit. So that's what I'm looking for. How far down did it get on its way to the wall? So just like before, I'm going to break this down into a horizontal and a vertical. This time I'm going to start with a horizontal. Last time I started with the vertical because I knew a lot about the vertical. I knew where the floor was. I knew its acceleration. Here, I actually know, well, relatively quite a bit. I know that it's going to move to the wall, and that's 10 meters away. I know that it is moving at a speed, or velocity really, of 250 meters per second, horizontally to the right. And, that's enough information, again, to find the time. I'm always interested in time in projectile motion questions because it links the two components. It links the x and the y together. So I'm going to use, again, v equals d over t. Solve for t. T is equal to d over v. Put my numbers in. 10 over 250. T equal to 10 over 250, which is 0.04 seconds. Great. So I know this thing will hit the wall in 0.04 seconds. Now, meanwhile, vertically, it's been falling. So let me kind of jump over to the y, switch colors here again. I don't consistently use any one color for x or y, but I like to use a different color. So in this case, I'll use red for the y. Let's see here. This bullet is not rising, so I'll let down be positive. I'm always extra careful about direction in the vertical. In the horizontal, I kind of did it without even saying it, but I was using to the right in my diagram as positive in the horizontal, actually in the previous example as well. But I have to be extra cautious with the vertical. So down positive, V initial, this bullet is going really fast, but it is 0 in the vertical. It was fired horizontally. When it comes out of the gun, it is not rising, it is not yet moving downwards, but that will start to change as it accelerates. In fact, here it is. It's accelerating down at 9.8 meters per second squared. This is an important idea too, by the way. It doesn't matter how fast an object is moving horizontally, the vertical doesn't care. It's going to accelerate down the same regardless of those horizontal details. So let's see here. VI 0, acceleration is 9.8. That's positive since I let down be positive. Time. Yeah, time is common. So I'm going to pull that 0.04 seconds that I just found from the horizontal calculation into the vertical, 0.04 seconds, and I can now find what I'm looking for. How far down vertically does it drop? What's the displacement in the vertical? So I can again use my kinematics equations. D equal to VIT plus a 0.5 AT squared. VI was 0, so I can disregard that. D equal to 0.5 of the acceleration, 9.8, multiplied by the time, 0.04, which we square. And just multiplying that out, let's see here, 0.5 times 9.8 times 0.04, which I don't forget to square. And I've got a number on my calculator. The answer to this question, 0.00784 meters. I'm going to call that the answer. And again, notice that that really is not quite 8 millimeters. It's a very, very small distance. My diagram definitely was exaggerated, but that's fine. The fact that this is so small, in fact, leads to a lot of confusion. A lot of people will see something very quickly moving, such as a bullet, and they'll fail to notice that it fell down over a short span of time like this. They'll think sometimes that it didn't fall because it was moving so fast. Meanwhile, it didn't fall simply because it didn't have much time to fall, or didn't fall far because it didn't have much time to fall. All right, let's do one more example. This third example is actually going to be a fair bit more challenging than the other two. In the first two, you'll notice that the horizontal velocity was 0 in the beginning. Not the case in the third example. So here we go. In this one, a ball is thrown up at an angle of 30 degrees above the horizontal from a height of 2 meters above the floor. Find how far it moves horizontally before landing on the floor. All right, a diagram. This one has a floor, and there's a ball that is initially, I'll just sketch that in, a ball that is initially 2 meters above the floor. Now, it is thrown 30 degrees above the horizontal. So I've got a 30-degree angle in here. And what's going to happen is this ball will go through a parabolic path. So it will, I'll just kind of sketch this in a little bit. It'll rise and it'll fall. It'll hit the ground somewhere. And again, similar to the first example, my job is to find how far it went horizontally before it struck the floor. Okay, now, this problem does have a projectile, a ball in this case, that is actually moving horizontally and vertically right off the get-go. So what I'm going to do is I'm going to have to resolve that velocity vector. Let's see here. Oh, and you know what? I just noticed a mistake I made. In making this example, I neglected to give a velocity of the ball. We don't have enough information to possibly solve this problem, so I am going to slip that in and pretend it was there all along. Let's say that the ball is thrown up at an angle of 30 degrees. Let me just kind of slip this in I can make up really any number I want. So how fast do I want to throw this ball? Oh, I don't know. Let's say at 15 meters per second. Perfect. Okay, yeah, it wouldn't be solvable. Obviously, if you threw a ball faster or slower, it's going to have an impact on how far it'll land away. So let's just slip that in there, at 15 meters per second. I am then going to add that to my diagram, 15 meters per second. And now I have enough information to work with. Okay, so that 15 meters per second is not in the horizontal, it's not in the vertical, it is somewhere in between. I'm going to resolve it into components. So here we go. I'm going to draw kind of a brand new diagram here just for that vector alone. 15 meters per second. That 15 meters per second has a component that is horizontal, and it has also a component that is vertical. Now, I do know that there's that angle 30 degrees in there, so I have enough information to resolve these, or this vector into its components. Let's start with the y first. Let's see here, that vertical arrow, the vector there is opposite of the 30 degrees, so I think sine will work nicely for that. Sine of 30 degrees is equal to opposite. Let's call it Vy. So Vy over the hypotenuse, which we know to be 15. That means that Vy is equal to 15 multiplied by the sine of 30 degrees. Now, I don't need a calculator for this one. I happen to know that the sine of 30 is 0.5. That's useful to know these little things. So 15 multiplied by that 0.5 is going to be a nice 7.5 meters per second. Yeah, no calculator needed on that one. Now, the horizontal, let's call that Vx, can be found with cosine. Cos of 30 degrees is equal to adjacent, so that's Vx, over the hypotenuse, 15. That means that Vx is equal to 15 multiplied by the cos of 30 degrees. Now, I actually happen to know the cosine of 30 degrees too, at least to a couple of decimals, but it's a more complicated number, so I'm going to totally use my calculator on this one. 15 times the cos of 30, which is very nearly but not quite 13, so 12.990. I'm not going to write down that 0, but I'm going to kind of be mindful of it that I haven't rounded off too early. It's 12.990 meters per second. Okay, so let's see here. I'm going to go back to my picture for a second here. That ball is going to rise before falling back down to the floor. So let's have a look at the vertical here. The vertical. Going back to my green here. In the vertical, now let's see, it rose and then it fell. I'm going to let up be positive this time. It's really my choice. I could have let either way be positive as long as I'm consistent with my usage of sine in it. So let's see here. If I let up be positive, the initial velocity vertical is the 7.5 meters per second. Now that is up, so positive. Meanwhile, it's going to accelerate from gravity. Now, gravitational acceleration is down, so I'm going to let that be negative 9.8 meters per second squared. It's negative because the acceleration is down, and I've let up be positive. Now, this next part is the part that a lot of students would kind of confuse on their first try at something like this. They'll often forget to account for the direction of the displacement. Going back to my diagram for a second, I see that the ball started at this level, that was interpreted as a scribble, and it ended up at this vertical level. It went down. So I am going to reflect that in my displacement down here. It went down 2 meters. The displacement is -2. All right, now I would love to know how long that took, because I can use that in my horizontal to figure out how far it went horizontally. Now, this one is going to require us to use the quadratic formula, just to warn you that ahead of time, because we don't have that VI of 0 this time. But other than that, it plays through very similarly. D equal to VIT plus a 0.5 AT squared. I'm going to put my numbers right in right now. D is -2, equal to VI is 7.5. I don't know the T, so it stays a T. Plus half of the acceleration, which is -9.8, multiplied by, again, there's my T that I don't know, squared. Let me simplify that a little bit. -2 equal to 7.5 T. Adding half of -9.8 is essentially subtracting 4.9 T squared. It's looking a lot more like a quadratic now. I'm going to put it in its standard form, in which we want to have the variable squared first, so that 4.9 T squared. Let me imagine that I add it to the left side of the equation. So it's going to turn into a positive 4.9 T squared on the left side of the equation. I'm going to subtract the 7.5 T to join it on the left side of the equation. And I have a -2 camped out, still sitting there on the left side of the equation. On the right side of the equation, I've removed everything, so it's equal to 0. I now have a standard form quadratic. If you've forgotten how to do a quadratic or don't know how to do it in the first place, I'm going to be having a separate video on that. Hopefully it's already up for you to take advantage of. Okay, but I'll get going on it here. The T can be found as, and this is a memorized process, the quadratic formula. I have to take these coefficients of 4.9, which is the A coefficient, -7.5 is the B coefficient, and -2 is the C coefficient. So I'm going to have to take the negative of the B coefficient, so it's already negative, so negative of it is going to turn it positive. Negative of the B coefficient. Now, quadratic generally gives us 2 solutions, so there's plus or minus, square root of the B coefficient squared. I like to do this on my calculator ahead of time, just to make it a little easier for myself. So I'm going to take that -7.5 and square it. It becomes positive 56.25. 56.25. So that is the B coefficient squared. Minus 4 times the A coefficient, 4.9, times the C coefficient, -2. All of that in the root. And finally, all of which is over twice the A coefficient. All right. Now, I have to solve this twice. Once with the plus, once with the minus. So T equal to, I'm going to grab my calculator, open up brackets for the numerator, 7.5. I'll try the plus solution first. Root of the following. So 56.25 minus 4 times 4.9 times -2. Close brackets for the roots, close brackets for the numerator. Divide that by, in brackets again, 2 times 4.9. All right, I get a T of 1.50, 3 rounded to 5 seconds. That was my positive solution inside of the quadratic. But there's another mathematical possibility, at least. T equal to, I'm going to go through the exact same process. Now, I've already got it on my calculator, so I'm just going to change that addition to a subtraction. Everything else is identical. So I get a, let's see here, 0. Oh, hang on, something's not quite right here, because this should definitely give me a negative, just from what I know of this. So let me check if I entered that in right. 7.5 and the root of the following, 56.25 minus 4 times 4.9 times negative. Ah, there's my mistake. Okay, caught my mistake right here, and that means that my previous was affected. I'm going to have to erase that right out here. I made a typo on my calculator. Fortunately, I can see it. Let me go back and fix it. Okay, so I accidentally had in there instead of a -2 in the end of the numerator, I somehow slipped and put a decimal 2 in there. So I'm going to put that negative in there. That should fix it. Sorry about that. My T from the positive, or from the addition solution, is 1.7622 seconds. Yeah, that should be good. And now fixing that, going back to my subtraction solution in the quadratic. Yeah, that looks a lot better. It's negative 0.23 162 seconds. Now, negative. Okay, now in this case here, a negative time solution doesn't really make any physical sense. We know it's going to take positive time to reach the floor, so I'm going to reject this solution as I know that t must be positive to get to the floor. So that means that I'm going to go with this one, the 1.7622. Okay, now to finish this off, I am going to get myself another page here to work with. I am going to go back to the x, so here we go, horizontal. What did I know about the horizontal? Well, I knew that it was going horizontally at a velocity, which I'm going to have to, again, kind of peek back to. So let's see, where am I at? There it is. Okay, so horizontally, right there, 12.99. So here it is, 12.99 meters per second. I know that it did that for a time of my positive value there, so that was just up here, 1.7622 seconds. So if we want to know how far it goes, we can just use d equal to v times t, and that is 12.99 multiplied by 1.7622, which is equal to, here we go, 12.99 multiplied by 1.7622. The final answer to this question, to three figures, 22.9 meters. And I am done that example. Okay, so that's it for projectile motion, the end of this tutorial video. I hope that you learned something from it. If you have any questions, feel free to email me, and of course check out some of my other videos on physics so that you can learn from them. Hope you enjoyed it. Thank you for listening. Bye-bye.